In the previous video, we covered the idea that the derivative of the position function, I just realized this should be the derivative with respect to t, of the position function gives us the velocity function. Right. We also covered that if you take the derivative of the velocity function, it gives us the acceleration function. Right. This lesson is about antiderivatives. It's about the fact that this process also works backward. Right. And so what that means is that if you take the antiderivative of the velocity function with respect to time, you will get the position function plus some constant c. And that constant c is a huge difference between the two of them. You need to remember that when you take an antiderivative, you're going to end up with a plus c. Right? Similarly, if we take the antiderivative of the acceleration function, we're going to end up with a velocity function. Again, plus c. So I've got the steps written out for this, so we'll show you the steps and we'll get into the two examples that we have. So first of all, steps to use antiderivatives in the kinematics problems. Short of it, take the antiderivative of acceleration to find velocity, or the antiderivative of velocity to find position, and in both cases, you need that plus c. The second step, the problem will generally give you information to find the value of c, and what that generally means is you're going to plug in some time and some velocity or position, and find out what the value of c is. And as a final comment, you may need to integrate twice if you're going from acceleration to velocity and then from velocity to position, and you do need to find the c each time. It doesn't mean it's the same c, you're going to get a different plus c each time. So we'll take a look at an example of that right now. So if an object moves along the y-axis with acceleration a of t equals 12t minus 4, I want us to find the velocity and position functions for the object if it's initially at rest and a y of 2 equals 7. So notice here that I actually gave you two different pieces of information. I said that y of 2 equals 7, and I also said that the object is initially at rest. And I know we've seen this before, we've done this previously in the year. I want you to remember, what does it mean that the object is initially at rest? And if you're up for it, pause the video, think about that for a second. You should be able to write that as a mathematical statement. You should remember that if the object is initially at rest, it means that its velocity is 0 at time 0. So in other words, v of 0 equals 0. That's what initially at rest means. Right? So we're starting with the idea that acceleration is 12t minus 4. And so it's sort of like, okay, if a of t is 12t minus 4, if I were to take the antiderivative of both sides, the antiderivative of acceleration is velocity, so v of t is, and if I do the integral of this thing, let's see here, this is going to end up being 6t squared minus 4t plus c. Now the question becomes, how do I find that value of c? Well, right up here we have information about v. We know that when I plug in 0, I'm supposed to get 0. So I can say 0 equals 0 minus 4 plus c, which means c is 0. It basically means that I can rewrite my velocity function. I can say, yeah, I knew my velocity function was 6t squared minus 4t plus c, but now that c is 0, so I could write plus 0 if I wanted. I'm just going to sort of stop there, right? This is my velocity function. This is half of the answer to the question, because it wanted the velocity function and it also wanted the position function. Right? So now that I have velocity, I can keep moving. Same deal as I did before. I'll take the antiderivative of both sides. We know that the antiderivative of velocity is position, so I could say p of t, but a lot of times we'll say y of t or x of t, depending on whether the object is moving along the x-axis or the y-axis. So I went with y of t this time. The integral here will be 2t cubed minus 2t squared, and then again plus c. Right? Now again, how do I find that plus c? Well, again, up here we were told that y of 2 equals 7. That means when I plug in 2 to the y function, 2 times 2, I'm supposed to get 7. So we can work through this thing. Let's see here, 7 equals 16 minus 8 plus c. 7 equals 8 plus c, which means that c has to be negative 1. So again, this means that I can refine my original statement. Before I knew that y of t was 2t cubed minus 2t squared plus c, and I can now say that that's minus 1. Now that we have these two functions, we could do anything with them. If they wanted to know the velocity at time 5, great, you could plug in 5 to the velocity function. If they wanted the position at time 5, great, you could plug in 5 to the position function. In the previous video, we covered the idea of how to find out if an object is speeding up or slowing down. The same thing could be applied here now that you have a velocity function and the original acceleration function. I have one more example of this where I'm going to do, one slightly different thing, so we'll take a look at that real quick. An object moves along the x-axis this time with velocity, so I give you the velocity function for time greater than 0, and it says if the object's position at time 1 is 6, find the position function for the object and then find its position at time 4. Realistically, all this should mean is you're going to take the integral, you're going to find c, and then we'll have the position function, which means we can plug in 4 to the position function. This really isn't anything new, so I would recommend you guys pause the video, run through this one on your own real quick, and then check the answer. Alright, so just like we did last time, we've got v of t is, and I'm going to do something interesting here. I'm going to write this as 5t to the negative 1/2, because I know I'm about to take the integral. I want to put this in a form that's easy to take the integral of. Right. So now I'll write the integral of both sides. So this is going to give me x of t because it's moving along the x-axis. Again, you could have used p of t if you wanted, but generally I'm going to use x of t and y of t if they're moving along the x or y axis. Equals. And so when you increase this power by 1, it becomes 1/2. We multiply by the reciprocal, so we're going to end up with 10t to the 1/2 minus t squared, and then again we don't forget that plus c. Now that I have this, I plug in the information that was initially given. They told me that when time was 1, the position was 6, so that means 6 equals 10 times the square root of 1 minus 1 squared plus c. 6 equals 10 minus 1 plus c. 6 equals 9 plus c. So that tells me that c has to be negative 3. So just like before, this allows me to refine my position function. X of t is 10 root t minus t squared minus 3. That's the position function, which is half of what they asked for. The last part was, what is the object's position at time 4? Great, so I just have to take this thing and plug 4 into it. So x of 4 is 10 root 4 minus 4 squared minus 3. Let's see here, so this is 20 minus 16 minus 3, which tells me that the object's position at time 4 is 1. And that's the end of the problem. And that's all I have in this video. I think I've got, there's one more after this that's really important, because there's a different way of thinking about how to do these integrals. So make sure you check them out. Like it's not, the next video is not the same thing as this one. There's a really, really neat trick that you can use for certain problems. So I'll see you in that video.